let's make a start. Chapter 2, Basic Single Degree of Freedom Systems. So what am I going to cover? Well, we'll talk about undamped oscillations first and foremost. This stuff should not be new to you, okay? Very basic, free, single degree of freedom system and a forced single degree of freedom system. I'm going to talk about complex notation. Again, it shouldn't be new, but it's really useful to really know this stuff well in this course, okay? Otherwise, you're going to lose track of where I'm going. So complex notation, I'm going to talk a little bit about how we use it. We use it because it's easy, believe it or not, to think about things in the complex plane. Then I'm going to talk about damped oscillation. The reason I've done complex and then damped is because I use the complex notation when I'm talking about the theory of damped oscillation. Free and forced. And then I'm going to talk about some alternative forms, different ways that we can write the same things that we're going to discuss in this chapter. Now in this lecture, this session here, we're probably going to stop before we get to forced damped oscillations. We'll see. I've got a few examples that we're going to do, okay, at certain points in this chapter. Okay, so we'll just see how we get on. We may end up doing the damped stuff next week, but we'll see. So, the simplest form of oscillation, when a system is undamped and free to oscillate, is called simple harmonic motion or simple harmonic oscillation. You should have all heard of that, okay? And in this case, the solution, which we call x is the displacement, it's a function of time, so it varies as time increases, is generally given by this sinusoid, okay? Cosine omega naught t plus phi, okay? Some Greek characters, omega naught. Well, omega naught is known as the angular frequency of the oscillation, okay? A is known as the amplitude, so that's the largest displacement from the equilibrium position. Now sinusoids, as you all know, go up and down, okay? And if, I haven't got a pen, but if they go up and down above, and sine of x will go up and down, with 0 being the mean position. It goes above x by a certain distance and down x by a certain distance. Well, A is basically the difference between that mean position, that 0 line, and the peak amplitude. It's not peak to peak. Okay, so make sure you remember that. Omega naught, like I said, the angular frequency of the oscillation, measured in radians per second. And then phi is what's known as the phase angle. We'll talk about this in a minute. But basically that compensates the correct position when t is 0. If we take omega naught as the angular frequency, okay, then the period of oscillation, which is the number of seconds for one period of oscillation, is given by 2 pi divided by omega. Okay? These simple equations can be derived, and I can do if you want me to, but it's relatively straightforward to understand. 2 pi divided by omega is the period, and 1 over the period is the frequency of oscillation measured in hertz. Do not confuse something given in hertz with something given in radians per second. They are different by a factor of 2 pi. 2 pi times f is omega, or f is omega divided by 2 pi. Okay, so if I say something's vibrating at 5 hertz, you need to convert it into omega by multiplying it by 2 pi. And there's an example with that. What's the basic, simple example? Well, we're all mechanical engineers, so it's a mass spring system. There are various examples in the electrical domain, but I'm not going to touch on them in this module. So here we've got a mass of mass m. It's on a frictionless surface indicated by the wheels. Okay, there's a spring of constant k. That's a linear spring. And when that line is at x equals 0, it's in equilibrium position. If you left it alone, it's not going to move. But if I extend the spring by moving it a distance x, which is indicated there, in the positive direction, which is indicated by the xt being in this way, then there's going to be a restoring force created by the spring that's going to try and pull the spring, or pull the mass back to the equilibrium position. And of course we know this is an undamped system, so it'll do so, it'll bring it back to the equilibrium position, but it will overshoot, and will then compress the spring. Now, because it's a linear spring, if you compress the spring, it's going to produce a force in this direction, which is again going to try and push it back to the equilibrium position, and so on. And it will just continue on going. There's no damping. Continue on going until I stop it with my fingers. What's the force in a spring? Well, we know the force in a spring is kx, or minus kx, minus indicating the fact that it's in the opposite direction to which you're travelling. Okay. Remember, spring forces and damping forces always oppose motion. So when you're doing Newton's second law, you must remember the minus sign. So Newton's second law, the sum of all the forces is mass times acceleration, here denoted by mx double dot. And all the forces being applied, well, there's only one force being applied to that mass, it's the spring force. It opposes motion, so it's minus kx. Mx double dot equals minus kx. Well, you can rearrange that, putting the kx on the other side, so you get mx double dot plus kx equals 0. And then if you could divide both sides by m, you get x double dot plus k upon m, x equals 0. Now this, as you should all be aware, is a second order differential equation. Okay? Like I said, there's some maths involved in this module. So how do we go about solving this differential equation? Well, one way to solve differential equations is to apply trial functions. Okay? And we can use our intuition here because we know that a simple, free, undamped system is going to vibrate in an oscillatory manner. Yeah? It's going to oscillate with the sinusoid as a function. And we know, therefore, that the solution is this, which is what we had before, providing that omega naught is root k upon m. So the solution is always going to be in this form, providing that omega naught, the natural angular frequency, is the square root of the spring stiffness divided by the mass. So if you've got a system that's going to vibrate freely and you know the spring stiffness and you know the mass, you automatically know the natural frequency. It will not vary from that position if it's free and undamped. Okay? Root k upon m. And that fits into this equation. So we've got A, which is an amplitude, cosine omega naught t plus phi. We know omega naught t because we know the stiffness and the mass. A and phi are what we call arbitrary constants, and that's because they can be found from initial conditions and initial conditions only. We can't determine them any other way. Doesn't matter. If you think about it, if I've got a mass and I move the thing by 1 millimetre, it's going to oscillate with an amplitude of 1 millimetre. If I take the same mass and the same spring, considering it's a linear spring, if I move the thing by 1 metre, it's going to oscillate with an amplitude of 1 metre. But that initial condition, whether I move it 1 millimetre or 1 metre, okay, is what I define to the system. And A will change correspondingly. But I can't work out A if I don't know those initial conditions. The same thing with phi. Okay? If I give it an initial velocity, I put it out half a metre, but actually push it, that will change how it oscillates, because it will change where phi is. We can check that that works. If we take that equation, this equation down here, this one, we take the second derivative of it, so we get x double dot, we can put that into this equation, okay, and solve, and we can work out whether we're correct that omega naught is indeed root k upon m. So if I take that, there's the second derivative. You take the first derivative, you get a minus a omega sine omega t plus phi, okay. But if I take the second derivative, obviously another omega comes out, so it's omega squared. And obviously I keep the minus sign and the sign turns back into a cosine. Like I said, maths is involved in this module. Second derivative, relatively straightforward to do. And so that's simply minus omega squared times x, because obviously the a cosine omega naught t plus phi is what we had originally. I stick it into that equation. So I've replaced x double dot with that, with the omega squared x. And I can solve, obviously, for x, or I can, in fact, I can't solve for x. X comes out of that if I divide both sides by x. And I can rearrange and we can find out that omega naught is indeed root k upon m. Okay, so there's basic free single degree of system, undamped. Some texts you find might write omega naught as omega n, okay, natural frequency. And that's fine, but there is a point later in this course where omega n I use for another thing. that's not the same thing as natural frequency. So that's why I've called it omega naught, which you will find in other texts as well. So omega naught is the natural frequency. The undamped natural frequency. So that's free oscillation. Okay, so we've covered basic. I'm guessing none of this is new to you guys. Yeah? It all makes sense as well? Are you all following? Please stick your hand up if there's something that you don't get, and I can go over stuff again. I don't mind at all. Okay. Force oscillation. Well, I've got the same system here. Spring, mass. I've moved the mass from the equilibrium position by a distance of x, but I'm also applying a force to that mass. Okay? I'm applying a force to that mass, and we're going to talk about in chapter 3 different types of forcing functions, but here it's going to be quite basic. So force is defined by f of t, it's a function of time, and in this situation, that's Newton's second law, mx double dot equals fs plus ft. Okay. Force of the spring minus kx, so it's a minus sign. F of t is in the same direction as x, so it's a plus f of t. And if I rearrange it, obviously you get mx double dot plus kx equals f of t. That's all very relatively straightforward to understand. Now in this case, I'm going to make the function of time a sinusoid. Okay? So I've got some amplitude of force. It's a cosine force, a cosine wave. And that cosine has a frequency that I'm driving it at of omega. Notice the lack of the subscript. Okay? There's no subscript. So that's this system, if I left it to oscillate on its own, would oscillate at omega naught. Okay? Omega 0. But this time I'm actually applying a force to it. Okay, and to start off with, it's not going to like it because it wants to oscillate at omega 0 and I'm applying it with omega. Okay? But after a while that omega term is going to disappear. Normal systems have damping and it will end up oscillating at omega. Okay? And like I said, omega is of my choosing. It's not of anybody else's choosing. I choose what omega is going to be. Omega does not necessarily equal omega naught. Things happen when they equal each other, and we'll talk a little bit about that in the future. But at the moment, let's assume they're different. When you're solving differential equations that are equal to a function, as we saw, okay, and we'll talk about this again in the future, there are two parts to that solution. Okay, one is the transient, which I talked about. The other one is as time goes to infinity, which I'm going to talk about here. Okay? One's called the complementary function, one's called the particular integral. We're just going to solve for that one as time goes to infinity, so we're not going to worry about the transient solution to start with. So we'll try our trial function. As we've done before, we know it's going to oscillate at the sinusoid, and we know in this case, like I said, that the sinusoid is going to oscillate at the frequency of my choosing, at omega. So this is the trial function, a cosine omega t. We can take the second derivative of it. Okay, so the minus omega squared comes out. We have a cosine omega t, so obviously a cosine omega t is x, so you could just say it's minus omega squared x. Remember, this is omega that I choose, not the natural frequency. And if you substitute that into our equation of motion, you get this. Okay. I've got a minus m omega squared, okay, plus the k, times by my x term up there, equals f naught cosine omega t. Now, because I've got a minus and a plus here, I've switched them around, so that quantity, I've not got a minus sign in front, so that's all I've done, going from this line to this line, just to change the way it's written. Now obviously from this equation I can divide both sides by cosine omega t. They're the same, obviously. If t is 10, then I've got cosine 10 omega on both sides, so that they disappear. Okay, divide both sides by them. So I end up with f naught equals a times that quantity k minus m omega squared. And so you can rearrange and solve for a, amplitude. And so the solution, I just stick a in where a was, and I end up with this as my solution. Notice this time that A is not adjustable, okay? I can't, no matter where I set the thing going, A is always going to be this. It doesn't matter what I set, where I start it going. Like I said, we're talking about time as time goes to infinity, this is the solution. Well, the system can't remember what happened when time was 0, it's at infinity, okay? So we don't need to worry about initial conditions in this case. This is the solution. Okay? We've got the force divided by the stiffness minus the mass times by the driving frequency squared. Yeah? At time equals 0, put 0 in here, you get cosine of 0, which is 1. And so at time equals 0, that is the starting position of that oscillation. And that's the amplitude of that oscillation. Okay? If I increase the force, the amplitude is going to go up. Okay? If I increase the stiffness, or increase the mass, or increase the stiffness, certainly the amplitude is going to go down. Okay? What happens to A as omega changes? Well, we can either think about it, use our intuition, okay, or we can just use the equation and try and work it out. Well, first off, let's use our intuition. At really, really, really low frequencies, okay, so I'm going to drive it with a frequency of 100 years, or 100 what is it, 2 pi divided by omega, so a really, really huge period of 100 years, okay. What's going to happen to A? Well, if you think about it, if I'm applying a very small frequency, okay, then basically the mass is just going to keep up with my position, and my position is going to be the force divided by K. Okay? That's known as the static solution. F0 divided by K. As omega goes to infinity, okay, so I'm really, really high frequency, the thing's not going to move, okay? Because I'm applying such a high frequency that in terms of the response, we're going to get 0 movement. Okay, so the amplitude is 0. And as I said, there's a special case, if I drive it at the resonant frequency, or the natural frequency, we get an infinite amplitude. Okay? That's why resonance is quite a bad thing. And I'll talk about that at a later stage. Now you'll notice that if we're driving at a frequency above omega naught, okay, so if this value is greater than omega naught, then you'll find out that when you solve the equation, K is going to be less than m omega squared. Okay, so obviously that's going to be negative, amplitude is negative. And so what will happen is, although you're driving it at that frequency, okay, so you're applying a force to that frequency, the thing is actually going to respond in the opposite direction. It's quite difficult to understand, but remember that there are a couple of ways to drive. You can actually attach something to the mass and drive it. Okay, the other way to drive something is to actually attach something to the wall and drive the wall, and the mass will respond. Well, in that case, if you drive it at above the natural frequency, the thing is going to respond in the opposite direction. Okay, level 2 dynamics labs last year, you would have been driving that 2 mass. Remember, you had a 2 degree of freedom system on the air track, and you were driving it by a pot connected to an elastic band. Well, that's exactly the situation I was talking about. Some cases, they're going to be driving in the same direction. The other cases, they're going to be driving in the opposite directions. And so if you were to plot amplitude over frequency, here, basically m is going to be, it's normalized, so m is the amplitude over the static amplitude. Okay, so static amplitude is when omega is 0. Okay, so obviously I get 1. And when omega, this is frequency ratio, so it's omega divided by omega 0. Obviously when they're equal to each other, I get a value of 1. When omega is less than omega naught, I get a value between 0 and 1, and obviously when it's greater, I get a value of greater than 1. And you can see that what happens is, up to the natural frequency, we have a positive amplitude that's heading towards infinity. I cross over 1 where amplitude is infinity, and I come back on the other side, and you can see that it's coming from minus infinity, and it's settling out at 0, the line connected to 0 on the y-axis. That proves what we've got going on. Before I move on to complex notation, which is the next section, I thought I'd do a couple of examples. Well, in fact, I'm just going to do one example. the two questions I chosen are so identical in the way that you solve them, I just thought I'd do just the one. And the example I'm going to do is question 1 from the exercises. I'm going to use the visualizer. Hopefully you can see it all, okay? The question reads, an industrial press is mounted on a rubber pad to isolate it from its foundation. If the rubber pad is compressed by 5 millimeters by the self-weight of the press, find the natural frequency of the system. Okay? Natural frequency, what are we trying to find? Okay? Question mark. We can think about this from first principles, okay? We've got an object that's resting on some compressible material. Okay? If we do a free body diagram of the object, we've got mg in the minus x direction, if we call this x equals upwards. Okay? And obviously that's being opposed by a spring in the opposite direction. Kx. So if we do the sum of all the forces in the x direction, it's going to be mass times acceleration in the x direction. And here I've got x, kx in the positive x direction, so it's positive, minus mg. The system is just sitting on the pad, it's not moving, so x double dot equals 0. So rearranging this equation, we obviously get mg equals kx. And we can obviously therefore say mg divided by k equals x. Now you'll notice on page 14 in the notes, we said that when omega is 0, okay, when omega approaches 0, so there's no oscillation, the amplitude of the oscillation was f0 divided by k. Well, here f0 is simply the weight of the machine. So it's exactly the same thing. Okay? Now we know omega naught is the square root of k divided by m. And so omega naught squared is obviously k divided by m. And if we rearrange this equation to solve for k divided by m, well, we end up getting k divided by m equals g divided by x. And so we can substitute into this equation g divided by x. So omega naught equals the square root of g divided by x. So that's the square root of 9.81. There's our value for g. And x, we were told, is 5 millimeters. 5 times 10 to the minus 3. So you do the sums. 9.81, 5 millimetres, divided by square root 44.2945 radians per second is the solution of that problem. Okay, so what I've done is I've gone from first principles. We've got our object on a spring. I drew the free body diagram of that object. I said x was upwards, arbitrarily, it doesn't matter. Okay, mg is obviously pointing downwards, that's gravity. Then kx is pushing upwards in the opposite direction. The thing isn't moving, so x double dot is 0. So the sum of all the forces equals 0. Obviously kx is upwards minus mg pointing downwards. Obviously those two things are therefore equal to each other. The mass is equal to the spring force because it's not moving. And you can rearrange to solve for x. Now I know that omega naught is the square root of k upon m. Okay? And if I rearrange my equation to solve for k upon m, I get g upon x. And so I can simply substitute g upon x into my omega naught equation, and I can solve for omega naught. Okay, which is what I've done here. And the comparison is on page 14. We said that if omega approaches 0, which in this case it is, there's no oscillation whatsoever, we know that A is going to approach F naught upon K, where F naught in this case is the force of gravity, it's the self-weight of the thing, which is mg, and obviously K has been given. So we've only been given one piece of information in that problem, that's the deflection at 0 frequency. So you think, well, how on earth can I go about solving for natural frequency? Surely I need the stiffness and the mass. Well, you don't need the stiffness and the mass. You need the ability to sort of think, hold on a second, what do I know and what can I work out from what I know? Okay. So in these sort of situations, it's worth going from first principles because then you can sort of understand what's going on. Question 2 is identical to question 1, it's just a slightly different. It's got a real world application. I think this it's a car deflects its suspension springs. It's exactly the same problem. Car of a certain mass, it's on its suspension springs. Here I've actually given you the mass, so there's going to be something else going on. But it's very, very similar. In fact, I don't think you even need the mass to solve for it. You don't. So that's a bit of a decoy, red herring, whatever you want to call it. We'll do question 3 in a bit. Right, has everybody got this down? Yeah? Okay, complex notation. You should be aware of complex numbers at this point in your degree. But I thought I'd just go over some basics and then introduce something called Eulers Relationship, which you should be aware of for this module, because we'll use it almost all the time. So here I've got a complex number, z. Okay? It's sitting on a unit circle in the complex plane. So my x-axis is the real part, and my y-axis is the imaginary part. Okay? Real is in the x-axis, imaginary is in the y-axis, and I've got z, which is sitting on the edge of the unit circle. The radius of the circle is 1. And so obviously if z is sitting here, it's got a value of 1. If it's sitting here, it's got a value of -1. If it's at the top, it's got a value of +j. There's 0 real part, but 1 unit of j. The imaginary part, and obviously down here is -j. And if we take the angle that that z makes with the horizontal axis, and we'll call that angle theta. And it's quite clear that depending on the value of theta, you've got a certain amount of real part and a certain amount of imaginary part. And we can use trigonometry to find out what those values are. Quite clearly, the real part is going to be cosine of the angle. okay? Because remember, the hypotenuse is equal to 1, okay? So it's 1 times the cosine of the angle will give us that horizontal bit. And then j sine of theta will give us the vertical bit. And so we can see that z, which is our complex number, is cosine theta plus j sine theta. Now this is where the magic comes in. A little bit of thinking about it. We know a clever chap called Taylor came up with a bunch of series for certain functions. And he said, and was determined, that sine of theta is equal to theta minus theta cubed upon 3 splash plus 5 theta to the power 5 divided by 5 splash minus and so on. Infinite series will give you sine. The same thing could be said for cosine, except for the values are slightly different. We've got 1 minus theta squared upon 2 splash plus theta to the power 4 upon 4 splash minus and so on. Okay? It gets even cleverer. Knowing that j squared is minus 1, j cubed is minus j, and j to the power 4 is plus 1, you can put the j's terms into these equations. So cosine, if we stick a j squared in, obviously that changes the minus into a plus. And then j to the power 4, well, that keeps the plus as a plus, because it's j to the power 4 is plus 1. And then for the sine, obviously we've got j sine theta, so it's j multiplied by the whole lot. But then if you multiply by j cubed, obviously j cubed is minus j, times by j is going to be minus 1. So that minus changes into a plus. And the same thing happens with j to the power of 5 times by j. That gives you j to the power 6, which is minus 1 times by 1. So it's minus and that changes into a plus. And so you end up you keep going, and you end up with a series of, if you add those two things together, you end up with this series. And it just so happens that this series equals e to the j theta. Okay? So our complex number, which is cosine theta plus j sine theta, equals e to the power of j theta. Okay? Why is this useful? Why is this useful to know? Well, what's the derivative of e to the j theta? Taking the derivatives of exponentials is very, very easy. Okay, that's one of the things that we're going to do. And I'll show you that in a second. Now, obviously, if we go back to that rotation around that circle, if we ignore the imaginary part and just take the real part, if we just look on the real axis of what x equals as the thing goes around a circle, okay, you notice that it's going to go backwards and forwards between plus 1 and minus 1 in an oscillatory manner. Cosine theta, that real bit, is an oscillation, isn't it? And so if we convert something to be in the complex plane, and we apply all our maths and all that sort of stuff, and then at the end of it take the real part, we've got the oscillation back, okay? If you think about that, if we've got something in the complex plane and you take the real bit, that means that this bit disappears and we've just got this bit back, which is the oscillation. And so what we can say is, instead of that being an angle theta, let's think about that in terms of an angular velocity, omega, in this case, times by time. We know that velocity is distance divided by time, or in angles it's the angle that you've gone through divided by time, gives you omega, the angular velocity. Obviously rearrange that, theta can be omega times by time. So we'll apply that. Omega equals, theta is omega times time. And so we can replace the theta term into my equation, and I get e to the j omega t, which is the complex form of a simple harmonic oscillation. You take the real part of this and you get that bit. Okay, the imaginary part is this bit. And for obvious reasons we can apply an amplitude to that and a phase angle to that. It's all the same thing. So wherever theta was, we've replaced with omega t plus phi. I've multiplied both sides by a. We can determine those things. And if you've got A equals e to the j omega t plus phi, it's very easy to find the first derivative of that, isn't it? You take the derivative of what's on top, okay, so that's going to be j omega, because j phi is 0, is the derivative of j phi is 0, and so you get j omega times a e to the j omega t plus phi. Second derivative, obviously the second j comes out, but minus 1, and you get an omega squared out of it. It's very easy. And then you take the real part of it and you get the oscillation. So we use that as a trial function more often than not. It's up to you which one you use, but it's quite often to use an exponential with j to some angle as a trial function, because that will give you the answer. Taking derivatives of exponentials is easy. You take the derivative of what the power is, okay, and then obviously you just repeat what was there to start with. And then you take the real part of that and you get x as an oscillation. X is a function of time. I wish I had a whiteboard marker so I could explain the derivatives, but if you've got any questions, let me know and I can cover it next week. So, that helps us with damping. Okay, it's going to be a classic example of where using the complex plane is a lot easier than trying to do it any other way. Damping. What do we know about damping? Well, there are two types of damping. Okay, there's a type of damping called viscous damping, which is a force on a system that varies as a function of the velocity. Okay, so if something's not moving, there's no damping. But if it is moving, it depends, the amount of damping force will depend on how fast the thing is moving. Okay? That's called viscous damping. The other term is called pressure damping, and that's going to vary depending upon the velocity squared. Now an example of pressure damping would be aerodynamic drag. Okay? That's a damping that depends upon velocity squared. As v goes up, the damping, or the frictional force associated with with aerodynamic drag will go up by v squared. Okay? It's why that travelling at 80 miles an hour uses quite a lot more fuel than if you're travelling at 70 miles an hour, despite the fact you're only travelling at a 12% more than you were beforehand, 12 or 13% more. Okay, so there's two types of damping. We are only going to be considering the viscous form. Okay, let's not worry about the one due to v squared. That's for another day when you've got too much time on your hand. We're just going to look at the viscous form. So it's to do with the velocity squared, and that's what this is shown here. We've got essentially a viscous damper is a piston in a closed cylinder, and there'll be some fluid in that cylinder, and in the piston, that's not shown in the diagram, you can imagine there's some small orifices, small little pipes, okay, constriction, and so as you push the piston, the fluid in that piston is going to go through those orifices to the other side. Very straightforward to understand, okay? But because of those constrictions, the speed with which the fluid can go through is generally going to be limited, and so you've got a force in the opposite direction from the way you're pushing, and that force is dependent upon the velocity you're trying to move it. Okay? That's represented schematically like this, a piston in a cylinder, okay? And obviously here I've got a velocity x and a velocity y, and it's the difference of those two multiplied by my damping constant c will give me the damping force. Okay? Obviously if one part is connected to a wall, then it's just going to be the other part that moves. Let's look at a mass spring damper system. So this is identical diagram to previously, okay? Except this time I've not only got a spring, but I've also got a damper C. So again, I pull the mass back a distance of x, I let go, the thing tries to return to equilibrium. But this time, instead of the spring opposing the motion as it's moving back, or in fact the spring at this point is applying a force to return it to equilibrium, I've got a damper which is going to oppose that motion. Because obviously for it to move, it needs to have a velocity, and if there's a velocity, that means there's damping associated with it. Okay? It'll overshoot, depending on the damping, okay? And obviously at that point, when the thing comes to a stop the other side, there's no damping force, but there's a spring force trying to bring it back, and so on. And what will happen is, as the damping is being applied, obviously with the spring we're getting the energy back, because we're compressing the spring the other side. Okay, with no damping, obviously you let go, the mass overshoots the equilibrium position, and all that kinetic energy in that mass is getting put back into the spring as potential energy. Great, and then obviously going the other way, it will convert that potential energy back into kinetic energy and so on. The thing is that the damping isn't taking any of that energy. Isn't giving back any of that energy. It is merely converting some of that energy into heat, generally, okay? And so what will happen is, although the damping is taking energy away, it's not giving it back, therefore the oscillation will reduce in amplitude and the thing will eventually come to rest. That's what happens with a car suspension system. You push down on the car, it might come back, overshoot a little bit, and then it will settle. If your dampers are short, it might come back, overshoot, go back down, overshoot, and so on, until it does eventually come to rest. So, let's take Newton's second law for this system. Sum of all the forces is mass times acceleration. As I said, damping will always oppose motion. So if we're saying x is in this direction, okay, positive x is in this direction, the thing is going to oppose motion when it's moving in this direction. Makes sense. Okay? mx double dot, mass times acceleration, is going to be the damping force minus the spring force. Okay? You move the damping and the spring to the other side, and we get mx double dot plus cx plus k plus cx dot plus kx equals 0. Another second order differential equation. Now, this is where there may be some new stuff. I'm going to introduce some terms that you may not have seen before, okay? And it's just an alternative way of analysing these systems, okay? We're going to talk about alternative forms at the end of this chapter, which will probably be next week, like I said. But in this case, I'm just going to talk about these alternative forms. And it's just a different way of thinking about these problems, okay? It helps in terms of simplification. If we say omega squared, omega naught squared, the natural frequency is k upon m, as we know. We've seen that before. And this time I'm saying gamma is equal to c upon m. So if I divide that equation of motion by m, I can rewrite it like this. Okay, so where I had mx double dot, I've divided that by m. Obviously that just means that we've got an x double dot. I will have c upon m, so I can replace that with gamma. And then I've got k upon m, which I can replace with omega naught squared. Okay, it's just an alternative way of writing that equation. I'm going to make a prediction. I'm going to predict that the system is going to oscillate at a frequency at or less than the natural frequency of the system. If you think about it, if there's damping, the thing's going to be a bit slower than when it's freely oscillating. Yeah? Well, does that make sense to you? As a sort of, trust your intuition. If the thing is going to have some damping, it's going to oscillate a bit slower than it would be if there was no damping. That's my prediction. And makes sense that oscillation is going to die out. Yeah? It's going to reduce in amplitude and will end up disappearing completely. That's what happens in real systems. We are aware of what will go on. If I set a pendulum in motion, okay, in this lecture theatre, depending on various factors to do with it, it will eventually die out. We live in the real world, okay? There's very few places where the free oscillation actually applies. Many approximations can be made using it, but here we're in the real world. So that's my prediction. Let's see whether it's true. Well, we've got to do some maths. This is a prime example of where using the complex plane is going to help massively, okay? So I've replaced x double dot and x dot and x with z. Z is my complex number, okay? And so my trial function, we've moved to the complex plane. I can use a e to the power of j, here I've called it pt plus alpha, doesn't really matter, to solve my differential equation. It's a trial function, that's how you solve differential equations. Okay, and it's a complex number, so I'm using that complex version. A e to the power of j pt plus alpha. Okay. Now if you look at this, p sort of smells like a frequency, doesn't it? If you remember the other things we were looking at, there was omega up there, so sort of it has a feeling of a frequency, and alpha has the feeling of of a phase angle. Sort of, we're familiar with it somehow. Well, we take the first derivative and the second derivative of that. Well, it's quite easy. First derivative, a jp comes out. So we have jp a ej pt plus alpha. And so obviously if that z equals this bit, then we can say it equals to jpz. And if you take another jp out, obviously j times j is minus 1. You get a p squared, so it's minus p squared times by z. Minus p squared over z. And we can stick that into our differential equation, the one at the top, to get that. So I've stuck those things in, I've taken out the z, and we've got this equation. Now the problem with this equation, there it is again, is that for this equation to be true, either z needs to equal 0, which is nonsense because z is the oscillation, the thing's going to move, so z cannot be 0. And for the bit in the parentheses to be equal to 0, the real bit needs to be 0 and the imaginary bit needs to be 0. Okay? You can't just say the whole lot equals 0 because you're comparing apples and oranges with pears. Okay? 0 is a complex number. We've got 0 plus 0j. Okay? And so to compare the apples, you take the real bits, and obviously they equal 0, and then the complex bits needs to equal 0j as well. But the thing is, let's take the complex part. Gamma j p. Well, gamma cannot be 0, otherwise there'd be no damping. Nonsense answer. J is obviously not 0 because we know what j is. It's the square root of minus 1. And p, do you remember we smelt the frequency? If there's no oscillation, i.e. no frequency, then there's obviously that's also a nonsense answer. So that can't be true. How can we solve this problem? Gamma jp cannot be 0. What about if we set p to be a complex number? So we're going to say p equals n plus js, where n and s are real. Okay. So this time we're definitely saying n and s are real. And so to substitute into that equation, for some reason it's come up with equation 4, let's not worry about it. I need to take that out. We plug those things into that equation, okay? So that's the bit in the parentheses. Sorry, that's not even the bit in the we just found p squared, okay? So n plus js, well p squared is going to be n squared minus s squared, because obviously you get js times js, or j times j is j squared, which is minus 1, s times s is s squared. Okay, plus 2j ns. If you did, like I said, if I had a pen I'd do it on the board, but if you took n plus js and you squared that quantity, you'd get this bit at the bottom. Let's substitute it into the equation and you get something that looks like that. Obviously the minus sign gives us minus n squared, that changes that minus to a plus s squared. Changes that plus 2jns to minus 2jns, and then obviously you've got minus gamma jn, which is up there. Minus gamma s, because obviously p is n plus js, plus omega squared equals 0. And we've, like I said, we've already determined that z can't be 0, so we've just taken it out of the question. So that's just the quantity in the parentheses. That's in this form. Now, it just so happens that we can solve that. The real parts can be set to be 0, and the imaginary parts can sum to 0, okay? So this is a good thing, we can solve for it. If we take the imaginary bits, minus 2jns plus gamma jn, well there it is, equals 0. Well the j's cancel out, and the n's cancel out, and so we can say that s is gamma upon 2. Straightforward. We've got s, so in this equation, we can stick it in there. So there's the real bits, minus m squared plus s squared, okay? We forget the 2jns, that's imaginary. We forget the gamma jn, that's imaginary. We've got minus gamma s plus omega naught squared equals 0. we substitute in our value for s, and you end up getting n squared is omega squared minus gamma squared upon 4. Now I know this seems like a lot of math, and I suspect many of you are sitting there thinking, whoa, this is too many Greek characters. I'm in dynamics, not Greek. Okay, that's fine, I understand. But take a moment at some point over the next week and just go over what I've been doing here, okay? It's relatively straightforward to understand if you just sit there and think about what's going on, okay? It's on pages 18 and 19 in your notes, okay, what I've been doing. And like I said, if you sit there and just go through it, step by step, you'll follow what's going on. There's nothing, it's merely algebra, essentially, okay? And I know that sitting in a lecture, just receiving it passively is like, oh my God, I'm not following what's going on. Like I said, just take a few moments at some point just to go over what's going on, and you'll follow what's happening. So at this point we've got a value for s, and we've got a value for n, okay? So we can substitute that back into our value for p, which is the complex number, remember, n plus js, and then the p goes into our trial function. So if you remember, we had our trial function was a, e, j, pt plus alpha. Well, here I've replaced the p with the n plus js, okay? And then I've separated out the exponentials. I've got here a, j times jst plus times e, j, nt plus alpha, okay? And we know s is minus gamma upon 2. We found that out. And n was that, slightly more complicated function, which we found down here as n. N is obviously the square root of that. So there's our solution in terms of z. And you can see quite clearly that what's going on. We've got an amplitude, okay, some arbitrary value depending upon our initial conditions. You have e to the minus some value times by time. Well, when time is 0, e to the 0, okay, is 1. We know anything to the power of 0 is 1. Okay, so we start off with a full amplitude. But as t increases, that term is going to decay from 1 down to 0, gradually, exponentially. Okay? As t approaches infinity, that term equals 0. So we can see straight away, if we ignore what's happening here, that term is going to start off at a times 1 is a, and as time increases along the x-axis, that term is going to decay down to 0. Yeah? So there's our decaying exponential. That's that bit. This bit here looks awfully like an oscillation, doesn't it? Yeah, if we take the real part of this bit, we get our oscillation. In this case, it's of a frequency n, but we're going to make one more substitution. So there we go, e to the minus gamma upon 2 times t is a decaying exponential, and that second exponential is an oscillation. We know from Euler's equation that e to the power of j times something is going to be an oscillation in terms of that something. Okay? We have j theta, j omega t, or whatever, it's going to have it's going to oscillate if we take the real part of it. And what I'm going to do is I'm going to introduce another term, omega d, which we're going to call the damped natural frequency. Omega d is n. So we've just replaced n in there, we get omega dt plus alpha. So if we go back to that equation for n, apologies, there it is, we can see that if this term here, gamma squared upon 4, is positive, and that would generally be the case, since gamma is a positive value, sorry, the gamma is C upon M, and C is generally a positive value, that term is going to be positive, okay? And if that term is less than omega naught squared, I'll talk about the other case afterwards, if that term is less than this, then the frequency, which we said is omega d squared, okay, is going to be less than the natural frequency. Our prediction was that was going to be the case. So you can see that it's working. And so, that's where we got to. There was our solution for Z. To get the oscillation, we take the real part. Well, the real part of e to the j omega dt is going to be cosine omega dt plus alpha. Okay? So we take this bit, a is just a number, arbitrary. E to the minus gamma upon 2 times t is just a number, again, depending on gamma, depending on time. It's just a number, it's not complex at all. And then this bit, we know that e to the j times something is an oscillation. If you take the real bit, you get the oscillation. And so that's what this is. So we've now got a solution for x of t. So if you've got a system that is oscillating, it's got damping, this is the solution to that system. If it's got no damping, think about it. Gamma, C upon m, becomes 0 upon m. So this term drops to 1, and you end up with a cosine omega 0t plus alpha. And that's the solution we had for the free case. So they work together, that you can understand what's going on. Okay? We have a decaying exponential times by an oscillation. And the oscillation is at a frequency omega d, which is less than omega 0. The damped natural frequency of oscillation. If we were to plot this, we get something that looks like this. Okay? So we've started it off at amplitude A, I've pulled it back, and I've let go. And the thing shoots off, heading towards equilibrium, but notice the overshoot isn't equal to the same amplitude. It's stopped there as opposed to down here. Okay? That's because for the whole travel, the damper has been taking away energy from that system and converting it into heat. Okay? But obviously that heat can't be then converted back into kinetic energy. And so it shoots off back, again, crossing the equilibrium position. Again, the damping's been taking out energy, so it goes less far, again. And so on, until the thing decays to 0. The dashed lines, that one, and that one just represent the boundary of the oscillation. And the frequency of oscillation, the period of this oscillation, say from here to here, or from there to there, okay, it's going to be 2 pi divided by omega d, not omega 0. It's going to oscillate at the damped natural frequency, which isn't the same as the frequency. It depends upon the damping you've got, okay? Notice that as the oscillation reduces, as it decays towards time, the period doesn't change. The period at this end is the same as the period at this end. It looks deceptive, but that's the case, okay? The period is going to be constant until the thing decays off to 0. You guys are all doing control systems engineering, is that correct at the moment? You'll come across this equation again, I'm sure of it. Okay? Or something very, very similar to it. And next week, when we introduce some alternative forms, you'll definitely see that, okay? Because there's some other terms that we use, sometimes more frequently. Okay, so, well, what have we got now? Well, that was the case for underdamped systems, okay? Where omega naught squared minus gamma squared upon 4 is greater than 0, okay? What happens if that term is less than 0? What happens if damping is so much that that gamma squared upon 4 ends up being greater than your natural frequency? But obviously that solution is nonsense, isn't it? You'd end up with a negative frequency. But fortunately, the solution isn't as far away as you thought. If we take that term and it's less than 0, you take the square root of that, you get plus or minus j times by gamma squared upon 4 minus omega naught squared. Okay, makes sense. You switch that around, you get a minus out of the front. Okay, you square root it, you get obviously plus or minus j times by that switched round. Okay, if you square this, you get that. Now if you substitute that value of n back into our equation, remember put that back into p, okay, so you get z, and then you take the real bit, you get this. Okay, I'm just giving it to you, you can take my word for it, or if you wanted to go through all the algebra just to solve it, you can do so, but I promise you that's the answer. Okay, and so you can see, just by looking at this, that we've got two decaying exponentials. Okay, e to the minus something times time, and e to the minus something times time. Now those values are different. Here we've got a plus between the two terms, here we've got a minus, so with two different decay times. And we've got two different amplitudes, A1 and A2. You can find them from the initial conditions. But what's going to happen is this thing is going to decay with respect to time. There's no oscillation shown in here. Where's the e to the power minus j something? Or j something, e to the power j something. There's no oscillation whatsoever. Okay, so the overdamped system, which is the case when gamma squared upon 4 minus omega squared is positive, okay, there's no oscillation. That's called overdamping. No oscillation in the solution, so you get a system that looks like this. There's line A, which I've drawn here. I've pulled the system back. It's a system that's overdamped. I've let go. It slowly accelerates, pulls away from my position, goes down, and settles at x equals 0, with no overshoot or anything, no oscillation whatsoever. The time it takes to settle at 0 depends upon your damping. Massively damping, it'll take a long time. Less damping, it'll take a shorter time. Curve B, what I've done is I've given it an initial velocity. So it starts shooting down, crosses over the 0 point, so it overshoots, and then settles to 0. There is no oscillation in line B. Oscillation would indicate that it would cross back over 0, then back over 0 again, and so on. There's no oscillation there. It goes overshoots, because I've given it initial velocity, and then will settle back to 0. This is overdamping. There's one more case, and that's where omega naught is gamma upon 2. So this is a case where that term, that n term, or omega d term, so let's go back to it, so where that term there equals 0. So the damping is such that the gamma squared upon 4 equals omega naught squared, okay? Or gamma upon 2 equals omega naught. And I'm not going to go through the derivation because it's just more maths, and by this point I'm sure you're tired of it. That's the solution. We have a single decaying exponential, okay? It's going to decay, and then we've got this term. And that's 1 amplitude plus amplitude times by time. Notice the t that's come in here. And so although the amplitude is going to grow with time, because obviously that's a linearly increasing term, isn't it? AT, as t goes up, AT must go up, A2 t. But obviously that increase is going to be killed by that decaying exponential. And so you end up guessing a decaying exponential. It's going to look a little bit like critical damping, except it's going to look a little bit like overdamping, except that the critical damping is the fastest way you can get back to 0 without overshooting. Okay? Because if you get a damping such that you overshoot when you let go of it at rest, you're under damping. Okay? So you're going to get to 0, but you're going to overshoot. And if damping is such that in the overdamped case, obviously it takes longer to get there. This is the fastest way to get back to 0 without overshooting or oscillating. Okay? That's called critical damping. And that's where I'm at today. Now, before you go, let's do question 3. in the notes. Okay, so the question says a mass spring system is found to vibrate freely at a frequency of 0.5 Hertz in a vacuum and 0.45 Hertz in a viscous fluid medium. Okay, so we've got some mass. If you let go of it freely, sits there, vibrates, 0.5 Hertz is the frequency of oscillation. You stick that mass with the spring attached into some fluid medium, water, oil, whatever, you set it going, vibrating freely, it's suddenly vibrating slower, okay? That's because the fluid is causing some sort of viscous damping. And the question says, find the damping constant, assuming the spring constant is 10 newtons per metre. Before I go on, there's a mistake in this question. The answer is wrong. We're going to find the right answer though. We've known that the answer was wrong. Let's go for the right answer. So, we've been given two frequencies. We've got the frequency, the natural frequency, F0, is 0.5 Hertz. So omega naught, we know, is going to be 2 pi times by the frequency, and so we obviously have 2 times by pi times by 0.5, so we've got pi radians per second. Okay, that's the frequency of that oscillation. We've been given the damped frequency. I'll call it FD. That's 0.45 Hertz. So to find the damped angular frequency, omega d, 2 pi times FD comes out to be 0.9 radians per second, 0.9 pi radians per second. Now, if you refer to equation 2.27 in the book, okay, so we'll write 2.27 here. You see that you have omega d squared equals omega naught squared minus gamma squared upon 4. And we've got to find the value for C. And you remember that we made the substitution that gamma is C upon M. So if we find gamma and we know what M is, we can find out what C is. Well, here's an equation for gamma. Great. What's M? We don't know. We don't have M. We're not given it in the question, but we are given the spring stiffness. And so we know we've got the natural frequency. That's pi. So let's find M first to start off with. Oh no, in fact, let's not find M. Let's work out what gamma is first. Let's do it this way around. So we take this equation and we want to rearrange it for gamma. Okay, so we multiply both sides by 4. No, in fact, I'll tell you what, let's move the omega naught onto the other side. So we have omega d squared minus omega naught squared is minus gamma squared upon 4. Let's get rid of the minus sign. That becomes minus, that becomes plus, that becomes plus. So we have gamma squared upon 4 equals omega naught squared minus omega d squared. Multiply both sides by 4, we get 4 times that, omega naught squared minus omega d squared. And then obviously square root the lot. So that equals gamma. Now we know that gamma is C upon M. And so we can say that C is going to be, I'll take the 4 out because the square root of 4 is 2, so it's 2m times by the square root of omega naught squared minus omega d squared. Okay? So this is what we're trying to solve. If we can plug in numbers for all of those things, we'll find C. Let's find M. We know omega naught, k upon m. So omega naught squared is simply k upon m. And we know that that equals pi. Yeah, we found it up here. Sorry, that's pi squared. We found it up here, there. We know k, we've been given that in the question, so m equals k divided by pi squared. 10 divided by pi squared is what we're trying to find. So let's plug in the numbers into here. 2, 10 divided by pi squared times by the square root of pi squared minus 0.9 pi squared, so going to be 0.81, sorry, 81 pi squared. Okay, 0.9 squared is 0.81, and pi is obviously pi, becomes pi squared. That's an 8, by the way, if you're having trouble reading my writing, apologies. So there's our values in, and in this form we can then stick that into our calculator. And if you do the sums, two, 10 pi squared divided by, then we've got pi squared 0.81 pi squared times minus square root times. I get 2.774. No, let's go for 50. Newton seconds per metre. Now, although the notes say this is something else, this is the correct answer, I promise you. Okay, so what we've done, we're given two things in the question. We said, free oscillation, the frequency is 0.5 hertz, okay? I've worked out the version in radians per second. When there's damping, the frequency is 0.45 hertz. So I've worked out the damped natural frequency in terms of radians per second. Equation 2.27 in the book defines omega d squared as omega naught squared minus gamma squared upon 4. We know that gamma is C upon m, and what we're looking for is C. We don't know what C is. So we've taken that equation, we've rearranged it to solve for gamma, okay? And since gamma is C upon m, I've rearranged it to solve for C. I've inserted this C upon m there, multiplied both sides by m, and we get this form, okay? M I can work out from my equation for natural frequency. We know that omega naught is pi, so omega naught squared must be pi squared, and omega naught squared also equals k upon m. We're given k, we can find m. So we plug that in the numbers and we get this as our value for C. Thank you very much, everybody. for your attention, and I'll see you next week.